Okay, so we are going through finite series. So far we have seen the definition of a finite series and we have seen some basic properties of finite series. Although we did not prove the properties, we will do that in the exercises. So today we are going to see that one can use finite series to define some things known as summations over finite sets. In this next definition, we are going to define what that means. Definition 716. Summations over finite sets. And the definition goes like this: let X be a finite set of n elements where n is a natural number. That means X is a finite set whose cardinality is n. We already know what that means precisely mathematically. Then and let f from x to r be a function from x into the real numbers. There is really no need to write that much. We can just simply write let this be a function. In this notation itself we can see the domain of the function and this other set also. But here the author is writing these things. In fact, he still continues, that is, f assigns a real number f of x to every element x of our set x. Then we can define the sum a sum which looks like this. We are going to define this sum as follows. Because x is given to be a finite set whose cardinality is n, literally using the definition of x having cardinality n, we know that there is a bijection between x and a particular subset of the set of natural numbers. So we are going to use that fact. we first select a bijection, any bijection actually, G from this subset of the set of natural numbers, the set of all natural numbers I which satisfy these inequalities to X. The fact that X has cardinality n, or more loosely speaking, X has n elements, means that there is at least one such bijection by the definition of finiteness of a set. And here the author also justifies that fact. Such a bijection exists since X is assumed to have n elements. Since our set X is assumed to have n elements. Now, using this bijection, we define our summation of f of x as x varies over our finite set capital X to be this series, this finite series f of g of I, where I varies from 1 to n. This is our ordinary finite series, what you see here on the right side, and this is the symbol that we are defining, and this is the definition. This is the meaning of this. Note that this is an ordinary finite series because here the thing that we are taking the sum of, that thing is a function of I. It depends on I. As I changes, it changes. It depends on I. It actually may not change, but in general it depends on I, and I varies from 1 to n. So this is our ordinary finite series, and we have a definition like this. Now, to understand what actually this means, let us take one example. Now, before we go to that example, let's just notice one thing. Although the set X can have any type of objects in it, which may not be numbers, but the fact that f is a function from X into the set of real numbers makes these images f of X real numbers. Okay. Of which we are taking summation, if you look carefully into the definition. Now this next example will make these things absolutely clear. Example 717. Let X be the 3 element set A comma B comma C, where A, B and C are distinct objects. Again, this need not be written actually. The fact that we have written that X is a 3-element set automatically makes A, B and C distinct. And let F from X into R be the function defined like this: F of A is defined to be 2, F of B is defined to be equal to 5, and F of C is defined to be equal to -1. Say this is the setup. Now, in order to compute the sum we will have to choose one bijection between X and the corresponding set here, and then we will define the sum like that. I mean, we will compute the sum like that. Now the thing is that we can in fact select any bijection as the definition says. So we decide to select this particular bijection. We select the bijection G from, you look at this set, this is the set of all positive natural numbers between 1 and n, including 1 and n of course. So here, just like that, because our X is a 3-element set, so we will accordingly have here the set of all positive integers starting from 1 and ending at 3. So that means 1, 2, 3. Where the actual bijection is this. G of 1 is defined to be equal to A, G of 2 is defined to be equal to B, and G of 3 is defined to be equal to C. Then so according to the above definition, what shall we have here? This will be equal to summation f of g of I, where I varies from 1 to 3. I mean the finite series, and this finite series is, we already know, equals this sum f of g of 1 plus f of g of 2 plus f of g of 3. Now this thing becomes f g of 1 is a, g of 2 is b, and g of 3 is c. Now you look at these values. This is 2 plus 5 minus 1, which is 6. Okay, so without thinking about what we are actually doing, we can just mechanically follow the previous definition and get this result. This is what the value of this symbol is in this particular case. But an issue arises here. The particular bijection G that we have chosen here is not necessarily the thing that everyone will always choose. Since the definition does not say precisely what bijection we have to choose, so it's up to us to choose the bijection. Someone may very well choose another bijection. What will happen in that case? So one could pick another bijection. I think I need ink. Give me a moment. One could pick another bijection say H from our set to X. Example, we can define H of 1 to be C, H of 2 to be B, and H of 3 to be A. One then has that same sum now according to that same definition, but with H in place of G, will be this f of H of I, where I, just like before, again varies from 1 to 3. So this finite series gives us what? F of H of 1 plus f of H of 2 plus f of H of 3. and that now becomes h of 1 is c, so f of c plus h of 2 is b, and this is a. And we already know that f of c is minus 1, f of b is 5, and f of a is 2. So we do get the same sum, 6. But this is only for this particular example, and that too only for these two particular bijections. I mean, as far as actually seeing whether the result is same, only in this particular case we can say that yes, the results are the same. But it has to be same all the time, because otherwise the definition does not make sense. If our final result depends on the choice of the bijection, then who knows, maybe if someone else chooses a different bijection, he may get a different answer. This symbol will then not have a fixed, definite, well-defined value. Different people may get different answers, and it will lose its mathematical importance. In other words, to say all these things more compactly, this would not be a very well-defined notion at all. Luckily, that is not the case. We always do get the same thing, and in the language of the things that we are going through, to verify that this definition actually does give a single well-defined value. Well-defined value of the sum we need to has to check that different bijections give the same result here. Different bijections from this set to X give the same result. So the actual sum is bijection independent. That's what we have to prove. In other words, we have to prove this next result, proposition 718. finite summations are well defined. And the statement goes like this: let X be a finite set. It starts almost like our original definition of finite summations, but instead of having one bijection we take two bijections. Let X be a finite set with n elements where n is a natural number. Again, there is a function from x into the set of real numbers. Let f from x to r be a function, and let we already have taken x, f, g and h be bijections, both are bijections from this subset of the set of natural numbers to x. Then we have this summation f of g of I, where I varies from 1 to n, is equal to summation f of h of I, where also I varies from 1 to n. Once we prove this, the definition of finite summation, summation over a finite set will be a well-defined notion. So now we will see the proof. And the proof is an induction proof on that natural number n. Inductions keeps on saving us so many times, and it will continue to save us. If a statement depends only on one natural number, and sometimes more than one natural numbers, then you may try to prove that by induction on that natural number. The advantage, I have already discussed about this, is that in an induction proof, the main hurdle is to go from the induction hypothesis to the next stage, which is to carry out the induction step. That is the main hurdle. But because in the induction hypothesis you have already assumed that the statement is true for some natural number n, so you can use the full power of that hypothesis to get to the next stage. And this often bypasses all the complexity that may be present inside the issue at hand, that is what is really going on in the background. You may bypass that and get an induction proof. The disadvantage is that sometimes you won't understand why something is true. Okay, you have proved by induction, but because you have bypassed the proof has bypassed the complexity, the underlying complexity, so you may not have the insight of what actually is going on or why the thing is true, but it helps us, so we keep on doing it. So let's now go through the proof. We use induction on n more precisely, this and that. Okay, let's just see what Professor Tao has to say. B. Use induction on n. More precisely, if we let P of n be the assertion, assertion means whatever we have here, he is again going to write that. For any set X of n elements, any function and any bijections G and H from this to X, we have in this case, it may look like an unnecessary thing to write, but sometimes things will get quite complicated in an induction proof. So it's better and it's advisable to exactly write down, or at least exactly have the statement P of n in your mind that you are actually going to prove. There are some subtle things here. If one is not very careful, one may miss these things. The statement P of n is this statement, which is after all a statement about this natural number n. But do you see this any? This thing means that this statement it depends on n, but at the same time it is telling us all these things for any set X on n elements, any function f and any bijections, everything taken together. Okay. Sometimes this part that something is true, you keep on thinking about n so much that you may miss these parts, that your hypothesis actually is much stronger than what you may think at first. Your hypothesis allows for you to change these things, G and H, X, this function f. Okay. F, however, in this context will not change, but the functions g and h and x itself, you can take some other set x also. For that also, this is the statement. I mean, that is included in this statement. More informally, P of n is the statement that proposition 7.1, is it 7 or 8? 8 is true for that particular n. Note that this is how we usually think of the situation when we start an induction proof. If the original statement is somewhat involved, it has many things. We think of the statement P and we are going to prove by induction like this, that the given statement in the proposition is true for that particular natural number n. But keep in mind that in the background all these things are there, that you can change g and h, you can change x, those things are there. And now what we are going to do, we want to prove that this statement Pn is true. P of n is true for all natural numbers n. So we first look at the base case, that n is equal to 0. We first check the base case P of 0. P of 0. In this case, so base P of 0 is what? Let's just again see that is the benefit of having this thing. P of 0 tells us that x is a set of 0 elements, and there is a function, that means x is actually the empty set, and there is a function f from x to r. If you are wondering what type of function can have the empty set as its domain, recall that there is a notion of an empty function. If you have forgotten, go back to the section where we dealt with functions. There you will see that we do have something known as an empty function. So we have that function, and there is a bijection g and h from this set where you do have this, in place of n you have 0. So can any natural number I satisfy these inequalities where in place of n you have 0? No. So that means this set in this case is also the empty set, and X is also the empty set, and G and H are two bijections from the empty set to the empty set, and both are actually the empty functions, and they are bijections. Okay, if you have doubt, you go back to the notion of empty function. There you will see that the empty function from the empty set to the empty set is actually a bijection. In this case, in fact, there is only one function, so G and H are identical. But what do we have to show in this case? We have to ultimately show that this thing is equal to this thing, where in place of n we have 0. So that's why instead of writing all those things in the beginning, we just simply write in this case by the definition of finite series both this series and the other one, which involves H, where I varies from 1 to 0, are 0, or rather I should write equals 0. That is because n is greater than m. So we have already seen in our original definition of finite series that in that case these series are defined to be equal to 0. So after all, they are equal, and that's what we want. So in this case we are done. And do you see one fun part about this P of 0 case? There is in fact no need to go through the hypothesis part of the statement P of 0, where you have that empty set, the function f and all those things, because P of 0 has this type of structure. No, there is something existence of x, existence of f, g, h, etc. Whatever you have here, that is the hypothesis, plural, of your statement. And your implication is, your conclusion, this is the hypothesis and this is the conclusion, f of g of I equal to f of h of I. Now you need to prove this is your P of 0, the structure of the statement P of 0. It's after all an implication, but these are the hypotheses, this is the conclusion. If the hypotheses are wrong, then the implication is automatically true, it is vacuously true. So you just assume that the hypotheses are right, and then you see what happens to the conclusion. But the conclusion here depends only on the fact that we have 0, and automatically, directly from the definition of finite series itself, both these things are equal and they are in fact 0. So you don't in fact have to think about the hypothesis in this case. Anyway, so we are done. Yes. Now we will assume that P of n is true. Now suppose inductively that P of n is true. For some natural number n, we shall now prove that P of n plus 1 is true. In order to prove that P of n plus 1 is true, we have to assume the hypothesis part of P of n plus 1 and prove that the conclusion part also holds. And for that, we are now going to take these things. Thus, let X be a set of n plus 1 elements f be a function from x into the set of real numbers. And let G and H be bijections from now this set to X. You will now realize why I was stressing back there about the word any. You have seen G and H in the original P of n statement. Now you are seeing G and H here in this statement. In that, for example, here in this induction hypothesis P of n, you have, if you write it out completely, you will see G and H. Those G and H are variables. Okay, they are not some fixed bijections. They can be any bijections. For any such choice of G and H, the statement P of n is true. That is the induction hypothesis. Now here in particular we have taken, again these are nothing fixed, but we have arbitrarily chosen some bijections G and H. If you want to make a distinction, you can call this G prime, H prime, you can give them some other names also. Now we have to prove summation f of g of I, where I varies from 1 to n plus 1 is equal to summation f of h of I, where I varies from 1 to n plus 1. And in order to conveniently be able to refer to this, let's just give it some name. Equation 7.1, the first equation of this chapter, which we are naming or rather numbering. Okay, now this is not something that we have written, and it is something that is true. We need to prove that it is true. Now let x be the image of I n plus 1 under the bijection G. Because G and H are both bijections from this set to X, so G of n plus 1 is small x, we are calling it small x, so small x is an element in capital X, our finite set. Thus if x is an element of X, small x is an element of X. Okay, now by the definition, of finite series, we can expand, because our original definition of finite series is a recursive definition. We can expand the left hand side of equation 7.1 as this. F of G of I is equal to summation f of G of I varies from 1 to n plus f of G of n plus 1, and G of n plus 1 is x, so plus f of x. Okay, this is pretty easy. We have just simply applied the definition of a finite series. It's raining heavily outside. So you may hear some thunders, some slight rumble. Now, next the author says that things could have been particularly easy if we had this. Now let us look at the right hand side of 7.1. Here Professor Tao says, ideally we would like to have, ideally we would like to have h of n plus 1, just like on this side you have g of n plus 1 equal to x, which is of course something you are just giving this thing a name, x. Now if it happens that on the right hand side h of n plus 1 is also x, it happens to be the same element in capital X, then things are particularly easy. Also, equal to x. This would allow us to use the inductive hypothesis P of n much more easily. Although here itself Tao does not say exactly how one can use the induction hypothesis and what is so easy about this case, but you will realize when we get to that stage. Anyway, we cannot assume this because there is no necessity for h of n plus 1 to also be equal to x. In general, it will not happen. That is just one of the many cases. But we cannot assume this. For now, just take the author's word for it that had this been always the case, things would have been much easier. However, okay, so in general h of n plus 1 is not x, but it is something. No, it is after all again like x, an element of capital X. Oh, that's not what we are after. Okay, we are now not going to concentrate on hn plus 1, but we are going to concentrate on x itself, because just like g, small h is also a bijection. So this x being an element of capital X will be the h image of something. So that's what the author writes next. However, since h is a bijection, we do know that there is some index j whose h image is also equal to x. Let's keep this equation for now. We do know that there is some index j with this for which h of j is equal to x. Do you see why? That is because h is a bijection from this set to x, and small x is coming from here. So because h is onto, h is an adjective map, small x will be the h image of something from here, and that something is j. That's why we have j. Okay, now all the arguments will revolve around j. We now use lemma 714. So this is that lemma where we have the basic properties of finite series. We use this lemma and the definition of finite series to write this. Summation. So we now concentrate on the right hand side of this equation 7.1. 1 to n plus 1, this will be equal to summation I varying from 1 to j f of h of I plus summation I varying from j plus 1 to n plus 1. It is one of the parts of lemma 714. I think the second one or the first one, I don't remember exactly. Now using the definition of finite series, this itself can be written like this. Using the recursive definition. Plus f of h of j plus of course this thing f of h of I varies from j plus 1 to n plus 1, and this becomes, this part of course stays how it is, this is what? H of j is x. So that means this is f of x plus, oh, I don't have space. I will continue here. In order to not confuse ourselves, let us just put one bar also here, plus this thing. Now in writing this thing, we are going to use one of the other parts of lemma 714, and instead of this, we can write summation I varying from j to n, but inside we have this. Instead of I, we have I plus 1. I ask you to go to the statement of lemma 714, identify which of the parts is being used here and exactly how. Okay. It's fairly easy to see what we have done here. You just go to that lemma and figure it out yourself. It's not very difficult. Okay, so that means the right hand side of our equation 7.1 now looks like this. Now define the function h tilde from the set of natural numbers from 1 through n into x minus x by this formula. H tilde of I is defined to be equal to h of I itself if I is less than j, and it is defined to be equal to h of I plus 1 if I is greater than or equal to j. We are going to do further calculations from this step, but here we have stopped temporarily because we need to do some things before. So we have defined a function like this. We will see why this function has been defined and what its use is. But now first of all we need to figure out that this function h tilde is first of all a well-defined function, and then that this h tilde actually is a bijection. It's a one-to-one function from this set onto this set. Okay, so let's just go through that now. Just like we need equation. It's a bit lightning. Just like we need this equation, we also need these things. So let's keep them also. B first. This part is not there in the text. The author asks us to verify on our own that H tilde is actually a well-defined bijection. We now show that this is a well-defined bijection. To prove that H tilde is well-defined, what do we have to show? If we take any integer from here, any natural number I, we need to show that H tilde of I, the way we have defined, actually is an element here, and that element is unique. For one I, we will get only one H tilde of I. If we manage to show that, it will mean that H tilde is well defined. So let I belong to the domain. If I is less than j, so one of these two things will happen. Either I is less than j or I is greater than or equal to j. So let's look at this case first. If I is less than j, then by definition this is equal to h of I. Now since our original h lands us in x, capital X, so h of I is after all an element in capital X. Note that since H is injective, that is 1 to 1, because recall that H itself is a bijection, although not from this set, from the slightly larger set where here we have n plus 1, but it is a bijection from that set onto the set capital X, not this one. So being a bijection, H is injective, that means 1 to 1. So since H is injective and I is less than j, we have H of I not equal to H of j, and H of j is x. I and j are different, so if inputs are different, for an injective function, the outputs are also different. So that means this image actually is not just simply in x, but it is also here. It's never equal to small x. Thus, this belongs to x minus x. And because small h itself is a well-defined function, so this h of I is a unique element here, a unique element in capital X for the given I. So that uniqueness already comes from H. Next, because we are going to show things about H tilde, so we cannot lose this also. So we have only for now this much space. Next, let I be greater than or equal to j. There is one more thing that I have not explicitly mentioned here. Note that because I lies between 1 and n, so that implies that I lies also between 1 and n plus 1, and hence I actually belongs to the domain of H. So H of I makes sense, because if I did not belong to the domain of H, small h, H of I would be meaningless, but that is not the case. Now next we have I greater than or equal to j. Okay, then we can only continue here itself. Then one is less than or equal to I plus 1. Already j is greater than or equal to 1. Now I is greater than or equal to j, so I plus 1 is even larger. So I plus 1 definitely is greater than or equal to 1. In fact, it is strictly greater than 1. But note that because I is coming from here, so I is less than or equal to n. So I plus 1 will be less than or equal to n plus 1. So I plus 1 belongs to the domain of our function small h. Hence h tilde of I, now in this case the definition is h of I plus 1, and this now makes sense because of these inequalities, and this belongs to x. Again, because I plus 1 is greater than I, which is greater than or equal to j, you see that again I plus 1 and j are different, and h is injective. We have h tilde of I, which is h of I plus 1, is not equal to h of j, which is x. So in this case also the image is not equal to x. Thus h tilde of I belongs to x minus x, and like before h of I plus 1 is also unique for given I, because h is well defined. Hence this is well defined. There is nothing wrong or problematic about the definition of this function. Now next we show that this actually is an injective function. For that we again, so we have seen this part, now the function is well defined. Now we need to show that it's injective or one-to-one. For that, let I1 and I2 be two elements in the domain of H tilde such that their H tilde images are equal. In order to prove that H tilde is one-to-one or injective, we now need to show that I1 is equal to I2. There are two ways. Either you assume this and show that I1 is equal to I2, or you can show the contrapositive. You can assume that I1 is not equal to I2 and prove that their H tilde images are not equal. And we have chosen to do this one. Okay, because you will understand in a given situation which one is the more convenient one to do. Here we have taken this one because we can immediately apply the definition of the function. Sometimes, however, it will be much easier to apply that other one. Assuming two distinct inputs, you show that the outputs are also distinct. Okay. If now some cases will arise. If I1 and I2 are both less than j, then H of I1 by the definition of H tilde is equal to H tilde of I1, which by our assumption is equal to H tilde of I2, which again by this condition equal to H of I2. Since H is injective, this implies I1 equal to I2. Okay, so we have what we wanted. If, let us look at another case. If I1 and I2 are both greater than or equal to j, then H of I1 plus 1 is equal to H tilde of I1, which by our assumption is H tilde of I2, which is H of I2 plus 1. Again, since H is injective, this implies I1 plus 1 equal to I2 plus 1, or I1 equal to I2. Two more cases are there. I1 is strictly less than j, but I2 is greater than or equal to j, and I2 is strictly less than j and I1 is greater than or equal to j. So let's take one of them and see what happens. So in these first two cases we have got what we wanted. But what about these new two more cases? Next, suppose I2 is, okay, let's take this one. I2 is less than j and I1 is greater than or equal to j. then h of I2 by the definition is h tilde of I2, which by our hypothesis is h tilde of I1, but because I1 is greater than or equal to j, that same definition tells us that this is h of I1 plus 1. Again, by the injectivity of h, so h of I2 is equal to h of I1 plus 1. So I2 is equal to I1 plus 1. Is it possible? It is not possible, because you look at these inequalities. If I2 is I1 plus 1, these inequalities tell us that I1 plus 1 is strictly less than I1. That is never possible. But this contradicts this thing. So that means our supposition is wrong. Let me just write all these things. So our supposition is wrong. That is, the case does not arise. The case does not arise under the hypothesis that h tilde of I1 is equal to h tilde of I2. Similarly, the other case will also lead to a contradiction. Does not arise. In the first two cases, we have seen that I1 is equal to I2. Hence, we have shown that in those only two possible cases, we have what we want. So we can now conclude, hence h tilde is injective. Now the next aim is to show that h tilde is a surjective function. It's an onto function. So for ontoness, we take an element in this set, show that it is the image of something here under h tilde. Let y belong to this. Then y belongs to x. Yes, y is not equal to small x, but after all y belongs to capital X. since our original function h is onto, we have y equal to hk for some k belonging to the domain of h, that is this set. Since y is not equal to x and x is h of j, we have k not equal to j. Okay. Now because k is not equal to j and k lies in this range, either k is strictly greater than j or k is strictly less than j. If k is strictly less than j, then also, before we write the conclusion, note one thing, that k lies between 1 and n. K already lies here, but k can never be equal to n plus 1. Why? That is because j is coming from here, so j is less than or equal to n plus 1. The maximum j can be is n plus 1. But even in that case, k is strictly less than j, so k can never be equal to n plus 1. So k will lie here. In other words, k lies here. And that is why we have y equal to h of k equal to h tilde of k. Note this condition, k less than j. Okay. So we have realized y as the h tilde image of something from here, and that's what we need for ontoness. But that is only when k is less than j. Now what happens if k is greater than j? K cannot be equal to j. Then if k is greater than j, then k minus 1 is greater than or equal to j. That is because k and j are, after all, natural numbers. Or you can write like this. And k minus 1 is less than or equal to n. Why? That is because k is originally coming from this range. These are the inequalities k originally satisfy. So k minus 1 will be less than or equal to n. So that means the thing now here is this: k minus 1 lies here between 1 and n, and at the same time k minus 1 is greater than or equal to j. So you can think of k minus 1 in place of I here in this second part of the definition and write, hence we have y equal to h of k equal to h of k minus 1 plus 1, and that is equal to h tilde k minus 1. So in this case also y has been realized as the h tilde image of something from here, and that something now is k minus 1. So in any case y is the image of something from the domain of h tilde under h tilde. Thus, or this shows that h tilde is onto or surjective. So being one-to-one and onto, it is a bijection. H tilde is a bijection from this set to this set, which is obtained from capital X by removing small x. Okay. Now we come to this thing, the right hand side. So we have done what we wanted to do with h tilde, but still we need h tilde for some more time. So let's just keep this and continue to use this space. We will now resume our calculation. That is, we will again start from here. So what were we doing here? This is the one way of writing the right hand side of 7.1. Hence, so let's just write this thing and free this space. F of h of I, where I varies from 1 to n plus 1, has been already shown to be equal to this. F of h of I, where I varies from 1 to j minus 1, plus, we can switch these two things because addition of real numbers is commutative. So we can write this one first, f of h of I plus 1, where I varies from 1 to, no, sorry, what am I writing? It varies from j to n plus f of x. Okay. Now next what we do, we use h tilde to change these sums in this way. When I varies from 1 to j minus 1, I lies here in this set and I is strictly less than j, and in that case h of I is the same as h tilde of I by definition. So this is h tilde of I, where I varies from 1 to j minus 1. And when I is greater than or equal to j, that is, if I lies between j and n, then again I lies here, but in that case h tilde of I is h of I plus 1. So in place of this h of I plus 1 we can write h tilde of I plus f of x. Okay, so with the help of this function h tilde, we have been able to modify this calculation slightly. Now you again use lemma 714 and you can write this sum of these two series, finite series, because here the index varies from 1 to j minus 1, here it varies from j to n as a single finite series. F of h tilde of I, where I varies from 1 to n, plus f of x. Now what do we need to show? We need to show that this is true, and we have already seen that this left hand side is actually this. This we saw in the beginning itself. Plus f of x. So that means we need to show that this thing is equal to this thing. Where, because we have the f of x term common, it's enough to show that this is equal to this. So we next write that this finite series is equal to this finite series. Thus, to finish the proof, of 7.1, we need to show that this series f of h tilde of I, where I varies from 1 to n, is equal to that other thing, f of g of I, where I varies from 1 to n. And let us give this equation also a number. Let's call it 7.2. Okay. Now you notice one thing. We have already proved, but in the text this has not been proved, that h from this set to x minus x is a bijection. Is a bijection, and something else is also a bijection, which is much easier to figure out. The function also the function g when restricted to this subset of the original domain of G, where I varies from 1 to n plus 1, here I varies from 1 to n. The function G is a bijection from this to x minus x. The author asks why. In writing that this this is h tilde. In writing that h tilde is a bijection, also the author asks why, but we have answered that why. We have actually shown that h tilde is a bijection. Here the author is asking why. If you look at the restriction of G to this subset, then that restriction is a bijection from this set to x minus x. Here tau is asking why, I am also asking why to u. So I want you to prove this, okay, this part. So what you have to do is just this. The original G is a function like this. It's a bijection. This G, this new G, which also we are calling G for the sake of simplicity, is the restriction of the original G to this subset, and the second set here is x. We are claiming that this restriction is also a bijection. Note one thing, that we don't have the input n plus 1 here. That is the only difference between these two domains. And we also don't have now small x, and small x is actually the output for the input n plus 1, because small x is g of n plus 1. So we have lost one input, and the corresponding output also we have lost. Everything else is same. Now you need to show that the bijective nature of the original G carries over to this new G also, restricted G. So we assume that this is the case and leave to you to prove this. Now what can we do with this new G and this h tilde? Note that h tilde is a bijection from this set to x minus x. The G that we are talking about here is also a bijection from this set to x minus x. And x minus x, because x has n elements, x minus x has n minus, because our capital X now has n plus 1 elements and x minus x has n elements, we are able to apply the induction hypothesis P of n, and that hypothesis directly tells us that 7.2 is true. Do you want to see why? You see, in the statement P of n, the x that you see in that statement is a set with n elements. In its place, now we have x minus small x, because our original capital X has n plus 1 elements. So you now have this set which has n elements. Its cardinality is n, and there is a function f from this into R, which is actually not exactly the original function f. The original function f is defined on the whole set capital X, but this function f that we see here is its restriction, okay, where we have restricted small f, the original small f, from capital X to this subset, which is obtained by removing small x from capital X. Okay, so we have one set having n elements, a function like that, and we have two bijections g. One of them is g, this restricted g, okay, not the original g, and another one is h tilde from this set to this set. So by the induction hypothesis P of n, by its supposed truth, this will be equal to this, and that's what we wanted to show. So the author writes like this: so these are all the hypotheses of the statement P of n for the case n. Oh, so back then I was saying that the function f in this context will remain the same. No, f also does not remain the same, because the domain size changes, no? So f also changes. So the author writes, since x minus x has n elements, and he justifies also by lemma 369. In fact, this lemma tells us that if we, from a finite set of cardinality n, if we remove one element, if the cardinality is not 0, if we remove one element, then the resulting set is also finite and it has cardinality n minus 1. That thing is lemma 369. Using that, tau is saying that this has n elements. However, we don't need to say this. Why? Because we have already shown that this is a bijection. So by the definition of cardinality, this set has cardinality n due to the presence of n here. But because tau left this part out for us to fill in, so that is why he could not have just simply written that this has cardinality n or it has n elements. So he decided to give a separate justification for that. But let's just keep it. So the claim follows directly from the induction hypothesis. So 7.2 is true, correspondingly 7.1 is true, and that's what we wanted to show. So this completes the induction and it also completes the proof. Now we can say, after doing so much, that the original definition actually gives us the same sum regardless of which bijection we choose to write the sum out or to compute it. So we have so far become absolutely rigorous, as rigorous as we can be in proving these things. So let's now be a little non-rigorous. Let's relax our rigor a little bit and see what is actually going on and what it is that we have actually done. You have a set X where there are objects A, B and C, and there is a function f from x to r, which I am talking about that example. And in that example, what were our values? F of A is 2, f of B is 5, and f of C is -1. We have defined this thing informally speaking. You really know what this is. You are taking the sum of all the f of x values, all the images of f, as x varies over x. So all these cases will occur, A, B and C, but in what order will they occur? That is, will you write f of A plus f of B plus f of C, or will you write f of C plus f of B plus f of A? You know that whatever order you choose to write this sum, it does not matter, because addition is commutative, addition is associative. I mean addition of real numbers. But you do have to choose at least one order in order to compute this sum, because and why do we need order? That is because we are trying to use finite series to define this sum, and that is why we choose some order. Now that order is given by a bijection, which will decide which one of these objects will be the first object, which will be the second object, and which will be the third object. In the first G that we have taken, our first object is A, the second one is B, and the third one is C. So we have f of A plus f of B plus f of C, and in place of A we have G of 1, in place of B we have G of 2, and in place of C we have G of 3. When we went to the other ordering, we decided to make C the first element, B the second element, and A the third element. This is our H. So that is why this is H of 1. H of 1 is C, f of H of 1 plus f of H of 2 plus f of H of 3. Okay. But looking at this thing, you already know that you are going to get the same result, but that is only an informal intuition, which nonetheless is true, but a rigorous proof needs to be a rigorous mathematical proof. That's why we had to go through all that hassle to get the proof. And moreover, in order to okay, and there is one more issue. It's not issue but an observation. Why did we use finite series to define such sums? That is because we already have finite series defined for us, and we also have listed some basic properties of those series. So if we use series to define this, we have one definition, and we have now proved that that definition is well defined. We will now automatically have properties, basic properties of finite sums corresponding to the basic properties of finite series that we have already seen in lemma 714, and whose proof you can imagine will directly come from the corresponding properties of the finite series. Now before we move on, I forgot to mention one remark which comes immediately after the statement of this proposition and before the proof. So let me just write the remark here. That remark is this: as opposed to this very nice situation where we can change the order of the terms in the sum in any manner we want, the infinite case is much more complicated, where you have an infinite sum. There, if you want to change the order, then things will not always be the same, and in fact many problems occur. So the author says the issue is somewhat more complicated when summing over infinite sets. See section 8.2. Well, there are some things. You see, we first got the notion of a finite series. Then using finite series, we defined summation over a finite set. We will in the next section go to infinite series. Using them, we can in fact define summations over infinite sets correspondingly, just like this. However, in that there will be some problem if you change the order of the terms in an infinite series. We will see, probably you already know or you have at least seen what infinite series is. So there, if you change the orders, then the sum may not always be computable. That is the first thing. And the second thing is that even when after changing the order the sum is computable, the sum itself may change. Okay. So we have the notion, something called absolute convergence. When a series is absolutely convergent, we can then change the order of the summands in any manner we like this one. But for series that are not absolutely convergent but conditionally convergent, the sum will change if you change the order of the terms. In fact, there is a result which says, which just gives us an idea of how bad the things are for conditionally convergent series which are not absolutely convergent. That result, if I am remembering correctly, that result we will prove in this text. It's due to Riemann. It shows us that if we have a conditionally convergent infinite series that is not absolutely convergent, then it can be made to converge to any real number, and it can be made to diverge to plus infinity or to minus infinity. I am saying some things, I am getting ahead of myself. Okay, I am saying some things which we have quite some time to reach, but still I am saying because some of you may have already got these things. So we will go through these things. The point here is that the infinite series, infinite summation cases are much more complicated than the finite ones. And after this proof, there is one more remark. And that remark is this. It's a purely notational remark. We are going to simplify our notation. Suppose that X is a set that P of X is a property or some sort of statement depending on X is a property pertaining to an element X of X, and f from X to R is a function. Not from the entire X to R, but rather from this set defined by this property, namely the set of those elements in X for which the property is true to R is a function. Is a function. Then we will often abbreviate this sum is he writing f of X? Yes. X belonging to this set This is also a finite sum over this set. We will, instead of having this cumbersome and difficult to write notation, we will abbreviate this to, or abbreviate this as this. X belonging to X, P of X is true. Which still looks somewhat difficult to write, or even as this, such that P of X is true if we know where X is coming from, that is, if the set capital X is understood from the situation, when there is no chance of confusion. When there is no chance of confusion. Now, if you think that this notation is also a little bit too much to write again and again, is true, in practice we never write is true. We just simply write the property P of X itself and assume that we are meaning that it is true. I mean, we are considering those X for which the property P of X is true. Most of the times we just simply write P of X and that's all. For instance, this finite summation f of n, or see, that's how we write. We never write that this property is true. We just write simply the condition. This is the shorthand for this sum. Which is f of 2 plus f of 3 plus f of 4, whatever f may be. Okay, now before I end this video, let me mention something which will come. Note that we have just a few moments ago, we have mentioned that just like we have used here finite series to define summations over finite set, we do have a notion of summation over an infinite set defined in terms of infinite series, and there we need something called absolute convergence. Now, do we do it just for its own sake, just as a new notion, or does it have any use? It in fact has a use for which in fact the author is doing it. You see, you may already know a fact which sounds like this: the set of real numbers is uncountable. What this means is that there is no bijection between the set of real numbers and the set of natural numbers, for example. Roughly speaking, what this means is that both the sets are infinite. We already have a definition for infinite sets, right? We know what finite sets mean precisely. We have defined all those things. And a set which is not finite is defined to be infinite. So R is infinite, and that is also something we have seen already. But the stronger fact is that not only is R infinite, but there is no bijection between R and N. And in fact, a much stronger fact than that is that there is an onto function from R to N, but no onto function from N to R. In that sense, R is more infinite than N is. The infiniteness of N is discrete: 0, 1, 2, 3. Okay, you can list the elements. The list will never end, but you can enumerate the elements. In R, that is not the situation. I mean, in its usual representation as numbers on the numbered line, no such enumeration is possible. So it is uncountable, and this fact often is proved using Cantor's diagonalization argument, using in the process the fact that every real number in this closed interval, for example, has a decimal representation which looks like this. Okay, 0 point something. Professor Tau avoids doing it like that. That is because we are not, we have decided in this text to do everything from scratch, right from the starting the piano axioms. Okay, from that stage itself, we are gradually developing all the things logically, as rigorously as possible. In fact, you have seen that while in other books, many things have been sort of proved in a hand-wavy nature, here nothing has been proved like that. Everything has been done. I mean, you can trace everything back to the absolute basic axioms from Zermelo-Fraenkel set theory. So the author gives a different proof. In that proof, that summation over infinite set notion is needed. There are other proofs of the uncountability of R also. There is a topological proof, but we are still far away from topological concepts. We are still far away from metric spaces also. These things will come, but it will take time. So our proof of the uncountability of R, we will see in chapter 8, I think, will be based solely on this idea of summation over infinite sets. Okay, so those things are coming. So with this, I end this video. If you want to say something, you can write in the comment section below, or you can send me mail at my usual address. The link will be in the description. So we have already done recently group theory. So this coming Tuesday, let us again do field theory from Herstein's topics in algebra. So that being said, this is it for tonight. So see you on Tuesday. Until then, this is me, Lucifer, signing off from a mathematical room. Have a nice night.